So good morning, let's get started. You hear me all right? So we are getting into the last part of the discussion on all the other atoms beyond the hydrogen atom. At the end, we will have a brief look at the periodic table. There's a very rich set of physics underlying what our discussion on atoms. The flow of today's lectures will be, the first thing is that we will discuss a nature's choice on the behavior of many electron wave functions. It happens that many electron wave functions must be antisymmetric with respect to interchanging two particles in the system. For the very reason that they are indistinguishable, but the choice of symmetric and antisymmetric, the easiest approach is to take it as an experimental fact. Although there are many theorems behind the so-called spin statistics relationship, but that is within the area of quantum field theory that is beyond the scope of our course. So that is the first thing that I would like to introduce. Then we will see how we can implement such a requirement within our idea of independent particle approximation. So the requirement itself, as summarized in this box on the first page, is good for any way you write down the many electron wave functions. For example, it could be a very complicated n electron wave function. But last time we developed some tools to reduce such an n particle problem into independent particle problems, but with some very fancy self-consistent scheme. So the second part will be to see how we can achieve this antisymmetric requirement within this single particle wave functions. The end result is very simple. There's something called the Slater determinant that gives us a way, a very handy way of writing down a many electron wave function. And from that point on, we will see that the Pauli exclusion principle that every one of you must have heard of in high school or in general chemistry is a consequence or a byproduct of this requirement, the one that you see highlighted on the first page. Another big consequence is that because of this requirement, and then we will take the example of a helium excited state and look at a profound consequence, which is a selection of whether the two spins of the two electrons should tend to align or tend to cancel out each other. It turns out that because of this requirement and the Coulomb interaction, there is a slight difference in the energies between aligned spins and cancel off spins. And that happens to be the microscopic origin of ferromagnetism. The reason that we have magnets to play with or to apply to various occasions. So it is a very fascinating one concept locked into another concept discussion. So let's get started. The first thing I would like to introduce is this box. So even if you don't follow 100% of what follows, this is the key idea. And that is nature's choice. So let me first give you the key result. Many electron wave functions must be antisymmetric. That is the term representing change one sign. So plus sign go into negative sign, that is called antisymmetric. So what have we done in order to change a sign? we interchange the coordinates of two electrons in an n electron system. So let me motivate this and make this thing reasonable. So what is the context that we are considering? So we are considering there are more than one electron beyond hydrogen. For example, 2 electrons in helium, 3 electrons in lithium, etc. Or even for bigger system, in a molecule, we have several atoms coming together to form a molecule. Thereby, we may have 20 electrons or tens of electrons. And even we have a piece of metal, 1 centimeter cube big. We can calculate, or we can use experiments to look at the so-called lattice spacing or lattice constant. Then we can calculate what is the electron number in such a piece of metal. A standard number is something like 10 to the 22 to 23 order. That huge number of atoms in just a centimeter cube of a metal. In all these occasions, we have electrons living in each other's vicinity. So that constitutes many electron systems. And the key point about this discussion is that the electrons are identical. Identical in Chinese is called 全同, 全同. And I think even more important is the idea of indistinguishable. 不可分辨的, 不可分辨的. In my opinion, I have an electron here in my office, and there's an electron on the moon. They are still identical. They have the same charge, they have the same mass, they have the same characteristic spin, angular momentum, which is always S equals half, etc. However, I believe if my electron is here, the other electron is on the moon, I can distinguish them by their locations. So the key idea about this requirement is more about the indistinguishability. When electrons live close to each other, microscopically, each electron is like a wave packet. If their wave function overlapped in their same region, in the same region that they live in, then they become indistinguishable. Meaning, we cannot label each electron by, say, this is the green electron, that is the red electron, and we can trace their trajectory. We cannot do that in quantum mechanics, and therefore, this idea of indistinguishability happens to play a very important role in quantum physics. So let's see what is the consequence. So in our simplest example of many electron problem is 2 electron problem, that is helium. But we could have that many in a piece of metal, or in the astrophysics context, you can easily have 10 to the 50 something neutrons in a neutron star that is something like a few kilometers in radius. And all this is related to what we are discussing. So next, let's appreciate what indistinguishability tells us about many electron wave function. Let's do the first discussion on distinguishable particles. This is a situation where you have one particle, this is a neutron, this is a proton living in a nucleus, for example. Then they are not the same. Although they live in the vicinity of each other, we can, for example, label them one as a red ball and another as a blue particle. So let's say we have a 2-particle wave function. I labeled it as distinguishable particles, superscript here. And let's take the consensus that the first entry, so it is a two-particle wave function. So the first entry gives us the red coordinate. The second entry gives us the blue coordinates, okay? So let's look at this situation. The red coordinates takes on R1, that is here. The blue coordinates takes on R2, that is here, all right? So you have a wave function of two variables. Now I put one variable, fix the number here, the second variable, fix it here, so I can plug it in. In principle, that is one value, right? You have a function of xy. You give me a xy, there's a number. Maybe complex, but there's a value, okay? Now, let's consider that I interchange the two particles coordinates. What does it mean? Let's consider the blue goes to here and it takes on R1, okay? That is to say, the second entry is R1, and then the red becomes here, interchanged it, and then it takes on R2. So the wave function that this situation refers to will be the wave function distinguishable. The first entry becomes R2, the second entry becomes R1, okay? Now, because they are distinguishable, these two situations are different situations. And we don't expect any relationship between them because they are different. So we don't expect this has anything to do with this, okay? Now, if the two particles are indistinguishable, we cannot label them red, blue, etc. They're just electron, okay? Now you can already imagine if I interchange the two situations, they refer to this. If I interchange the coordinates, they refer to the same situation. Thereby, we will expect some relationship between such a situation and the other situation, okay? So this is just to warm up. I know that some of you are doing the thermal and statistical physics course. So just to make connection to your other course, for the case that we consider as a warm-up example, distinguishable particles, in thermal physics, you will encounter such a game, a counting game. For example, you have two distinguishable particles. I draw it as a blue and a red, okay? Even if you use black and white, you can distinguish them. Now, each particle has a spectrum, energy spectrum. For it means a particle can carry low energy, 1 unit, 2 units, 3 units, etc. So for those who are doing Professor Go's course, have you gone to this place about microstates? Not yet, but soon, very soon, because that is the very beginning, the first thing in the statistical physics part, okay? Now, so keep this in mind when you go into Professor Go's class later, all right? Now, if the whole system of two particles has a total energy of no energy, 0, the question in thermal and statistical physics is, how many ways can you arrange the two particles to get that? Now that is easy. Two distinguishable particles, you can put the blue one into no energy state, this one, all right? The red one also into this thing, then the total system has no energy. Okay, so this is called a microstate of this macro state. So this is thermodynamics internal energy U. Okay, in thermodynamics, you don't look into the system about the microscopic constituents in the system. In statistical physics, we want to start with microscopic viewpoint and try to see whether we can get thermodynamics out of it. And now, another situation will be quite different if the particles are distinguishable against indistinguishable. For example, total energy 2 units. How many ways you can arrange 2 different particles, distinguishable particles, to get this internal energy? All right. So now you can think about it. Blue here, no energy. Red 2 units. That adds up to 2. Okay. Or red, no energy. Blue, 2 units. Also okay. And then each particle carries 1 unit of energy. Also okay. All right. Now, look at these 2 situations in particular. Because they are distinguishable, these 2 situations are different situations, right? Imagine if these particles are indistinguishable, they are represented by the same black circles, for example. All right. These 2 situations should be only counted once instead of counting as 2, right? Because it is black, no energy, another black for 2 units. You see, distinguishable and indistinguishable particles in this statistical physics context already refer to quite different behavior. You have to count this number, and then Boltzmann told you that K log this number is your thermodynamic entropy, and that is the beginning of statistical physics. So here you immediately see from a very simple game, counting game, the difference between distinguishable particles and the indistinguishable particle cases. Let's get back to quantum physics. Now we consider the same situation, but with 2 indistinguishable particles. We have the same setup. First coordinate is A particle. Second coordinate is B particle. Now, one situation, we have A takes on R1, B takes on R2. The other situation after you switch the 2 particles is B takes on R1, A takes on R2. But since they are the same particle, indistinguishable particles, you look at the situation, it simply say one is there and one is here, another is there. Okay, you switch them, it is still one is here, one is there. So we expect some relationship between this number. It is a wave function of 2 variables. There are 2 numbers plugged in. It should give out a number. So this function as a number has something to do with this other number calculated out when you switch the 2 entries. In quantum mechanics book, it is often written simply as such. So it is R1, R2, and then R2, R1 in the other situation. So we have one value here. We have another value here. We look at the 2 situations. They are the same physical situations, right? Thereby, because they are indistinguishable, thereby same situation, there must be some relation between this situation, this value, and that value. And that is related to the symmetry property of 2 particle wave functions. we will use the argument in two particle wave functions and then just take it to the n particle situation. So in simple terms, the two situations refer to the same thing in the way that it says, one particle takes on this coordinate, that place, and another takes on that place, okay? But the whole point of indistinguishable particles is that the punchline is we cannot tell which particle is which because we cannot distinguish them, all right? Now, to contrast the importance here, all right? Hydrogen atom, we only have one electron only. We don't need to consider all this thing, just a lonely electron. There's nothing to switch the electron with. And we have seen spin of that lonely electron plays some role. We have studied spin-orbit interaction, leads to fine structure that has to do with spin. Okay, we have also studied the relativistic correction. After you hand in the problem set 3, I hope that at least you know what is the Dirac equation that has some spin built into the equation. So spin also plays a role there. And then the spin magnetic dipole moment will interact with the external field in the Zeeman effect. So we have looked at what spin, the role that spin of the electron plays in hydrogen atom. As an advertisement of what follows, you will see the spins of many electron systems play a more important role than the spin of electron in hydrogen. In hydrogen, the spin of electron always gives us some perturbation, a little bit of effect beyond the typical, the standard hydrogen atom problem. But here, as you will see, the spin of the electrons has a big role to play in obeying this anti-symmetric requirement of many electron wave function. So it's just an advertisement. You will see the detail later. So let's continue. So in a more general situation, so this is a nucleus. Again, I try to depict two electrons. One is here. So what it means is that an electron is here at R1. And let's say we also consider the spin of the electron. It has spin up. And the B is here. So it is at the location R2 and the spin is down. So this is one situation. Now, if we interchange the two electrons' coordinates, what we really mean is the following. This one will go to here. All right, so what does it mean? Spatially, it means B will go to the new position R1, but in the spin context, it will also take on the upspin. Similarly, when A and B switch comes to here, it is at the location R2 and take on the spin down, okay? So now, if we do such an interchanging of the two particles, we have the same physical situation. And thereby, we follow textbooks notations. We will not write down the R1 and then with some spin coordinate. Most textbooks, nearly all of them use this. So 1, 2, this is the first A particle, this is the B particle, interchange them is 2, 1, all right? And we expect there is some relationship between them simply because before and after interchanging, they are the same situations. And in this discussion, I will use the simplest plausible argument. Remember, there's a Born interpretation of the wave function. It relies on the wave function square. Last time, we introduced it that when we have n particle wave function, what is the physical meaning, right? The probability interpretation still holds. So what we expect, the relationship is that this is one situation, switch step is another situation, it's the same thing. So the probability of finding one particle here, another particle there should be the same, okay? Thereby, the relationship naturally is phi12 absolute magnitude square equals phi21 square, okay? So this is the physical requirement as we anticipate by using Born's interpretation. And this is as much as we can say using what we know about quantum mechanics wave functions. If you still can't see what is going on, it is educational to look at what this equality means. The easiest thing is to plot some graph, all right? Now, but if you look at this thing, if this is x, y, z, this is another x2, y2, z2, there are 6 variables. And if I want to plot this, this is the 7th axis. So I need a 7-dimensional plot in order to do this, right? Impossible for me. So let's think about something easier. If I have 1-dimensional system and 2 particles, they only live on this line. So one is x1, one is x2, and so on. So this is the axis the 2 particles can live. And then one particle takes on a coordinate x1 equals a here. Okay, that is one position. Another takes on b. So x2 is b here. Okay, that is the case here. Now, if I switch the coordinate of the 2 particles, the wave function should become phi b comma a, right? If you have a function of 2 variables, this will give me one number, this will give me another number. And now we can imagine we can make a plot. This axis is a 3-dimensional plot, okay? But in a cartoon way, drawn on a 2-dimensional piece of paper. But our brain is good enough to visualize this. But 7 dimensions, sorry, cannot do that. Now, so this is x1, this is x2. The 3rd axis is the probability density function, phi x1, x2 squared, okay? Now, let's look at a case. For example, what is this point? This is x1 equals a, x2 equals b. So it is this one, okay? So here, if I look at a top view, look down, there will be a number here, all right? Or in the 3rd axis, there is a height representing of the magnitude of this square. Now, if you switch the coordinates, it means we look at another point. x1 is b, x2 is a. That is this point. All right? Now, what the statement says here, the square is the same. It means this number must be equal to that number. Is that clear? That is what the physical requirement says. The square is the same. Another example is written here as the circle. So this is another x1, x2, you switch it, it corresponds to this place. The two values of this phi square should be the same here. But no one says the value here equals the value there. That's not the case. There's no rule about this, okay? So what it says is that if you plot this 3D plot, you should see some, if I draw a diagonal, this is the x. This is the x1 equals x2 diagonal line. Okay. It looks like it is a mirror. Above it, on that side of the diagonal mirror, the number is the same as the equivalent place on the other side of the mirror. That is what this phi 12 square equals phi 21 square means. Okay? So what are the possible consequences? We have two choices then. Phi 12 equals phi 21, or phi 12 equals minus phi 21. So let me introduce some name. For this case, we call the wave function, two-particle wave function, is symmetric with respect to interchanging the two particles' coordinates. These coordinates, generally speaking, include the spatial x, y, z, and also the spin. And then for this one, with an alpha sign, that is called antisymmetric with respect with interchanging two particles. So what happened to electrons? From my viewpoint, I would say it is an experimental fact, or nature makes a choice. For electrons, all many electron wave function must satisfy the antisymmetric option. But nature is very clever. It also makes this option, but for another type of particles called bosons. In fact, all fermions, not only electrons, obey this antisymmetric requirement, and all identical indistinguishable bosons would have to obey this situation. Okay, now that has profound consequence. So if you have a gas of rubidium atoms, for example, then you cool it down to very low temperature, as in Professor Wang Dajun's laboratory. There's something called Bose-Einstein condensation occurs. And that has to do with this requirement for bosons. But we are talking about electron wave function. So nature makes this choice for electrons. That is the take-home message. So let me summarize one more time the take-home message. Nature makes a choice. Many electron wave function must be antisymmetric with respect to interchanging to any two particles. Now, I must state one more time clearly what I have been doing. I simply use the two particle situation to make this statement reasonable. Extending the argument to n particle wave functions is more involved than what we just discussed. You have to do something more abstract, like permutation operator. You take any two and then interchange them. But then when you have 10 particles, you can do 1 with 3, 2 with 7, all these permutation operators. But I think it's unnecessary because the key point is nature makes the choice. We have to look into the consequence. So the box equation 43 summarizes the most important part. We will look into some consequences, but at the outset, let's be very sure. This is a higher level requirement. What do I mean by that? It does not matter how you represent the n particle and electron wave function. This must be satisfied. You can work out the real many electron Schrödinger equation solution, and yet this must be satisfied. Or we can go into an independent particle approximation. Even then, we must satisfy this requirement. Okay? So one way or another, we need to play with this requirement. And this page is optional for those who fancy knowing more about what was happening. Some student has sharp eyes and wonder, how about this? This also works, right? If I take the absolute square and then this EI5 give me 1, right? First thing first, nature does not make this choice. But however, some human physicists, they can actually artificially make some systems in which electrons behave in this way of some chosen phi. Nature only makes 2 choices of phi. You can think of it as phi equals 0, phi equals pi, all right? But now, in some 2-dimensional electron gas system, you put 2 semiconductors, like 2 pieces of bread together, there's an interface. In this interface, we can put some electrons to leave them there freely. They move around, but only in a plane, okay? And you apply some, well, quite high magnetic field there. You control the magnetic field, the flux, so-called, and then you can construct different values of phi, and they are called anyons. I think in Cantonese it's called 任意子. You can Google anyons, you can find a lot of fascinating things. But let me state one more time. Nature does not make this choice. At least we have not discovered that it makes this choice yet. And then another big consequence is that we will see in the helium excited state, this antisymmetric requirement will have a big consequence. It has to do with ferromagnetism. Another point I would make in this optional remark is that if you look at the helium atom Hamiltonian, you already started to see that there is something related to interchanging of the 2 electrons. Imagine you replace all the R1 by R2 and R2 by R1. We see that this Hamiltonian of a helium atom has not been changed. Okay? So it is like what you learned in the last semester about some symmetry in the Hamiltonian. Therefore, for example, you can imagine if I have a permutation operator of interchanging the 2 electrons coordinate that commutes with the Hamiltonian, thereby you can look for simultaneous wave function, simultaneous eigenstate of these 2 operators, etc., etc. I avoid such a discussion here. I just want to make sure that you have this sense. Interchanging 2 indistinguishable particles, the wave function has some relationship, and then for electrons, it is antisymmetric with respect to this operation. That's enough for our purpose, okay? And that is what I just told you. If you want to go deeper, you want to into n particle situation, it is more involved. You need to have some funny operator interchanging things. And then if you want to read more, you can go to standard chapters in the standard quantum mechanics books, Rear and Branson. It gives a very detailed discussion, but more than we need. And even go deeper, Pauli, I think in 1931 or so, he has a theorem relating the spin of particles to the statistics or fermion-boson difference, but he relied on quantum field theory. But more practically, let's look at some fascinating things. Next question. Now we know the requirement, antisymmetric. How can we realize this? How can we achieve this within independent particle approximation? Okay, so that is the question. All right, now let's look at the ground state, simplest thing. Last part, we look at helium ground state. We did variational calculation per first order perturbation quite successfully. But in our discussion, somehow we don't include spin into our discussion. And you may say we are lucky, and now we are looking at why we were lucky. We don't need to consider that in our previous calculations. So let's see what is the spin, the role of spins. We have 2 electrons, so 2 spin half. What are they doing? So now we are talking about the ground state. Let's think about just hand-wavingly what's going on. We expect the 2 electrons will be both in 1s, and we think 1 electron is in 1s up with up spin, and another is in 1s but with down spin. And in general chemistry, this is the picture that you often see, right? Now, what actually is this? Picture refers to in real quantum mechanics. After you do the independent particle approximation with single particle states, thereby when we talk about 1s, we know what it means. We have a radial wave function, n is 1, L is 0, that is 1s, and then y 0, 0, theta phi, which is just a constant. So formally, we know this part. So let me introduce a name now. This is the spatial wave function, or the spatial part of the 2 electron wave function. Implicitly, it means there's another part called the spin part. We have to consider that the total wave function of 2 electrons must be antisymmetric. That is the new rule that we learned today. We want now to implement it in the ground state of helium atom. We are doing Schrödinger quantum mechanics. Thereby, the spin state, spin up, spin down, has to include into the Schrödinger solutions by multiplying into it the spin part. So we can represent the 1s with up is such a state, or in quantum number, it is n equals 1, L equals 0. Okay, ML equals 0. And then spin up is MS equals plus half. Or in chemistry context is often written as phi 1s, it is this thing. And then the spin wave function is alpha, that is the column 1, 0 in the matrix representation. 1s down is this thing, or 1s beta. So there are more than 3 quantum numbers when we include spin, that's the point. So what is the ground state in our mind? 2 particles both in 1s. The spatial part would be phi 1s R1, phi 1s R2, that will form a two-particle wave function, all right, R1, R2, and depicting the idea that we have in mind. Both electrons are in 1s, all right? Now, let's look at the symmetry property of this spatial wave function. This is related to the spatial part, x, y, z. We interchange the two. R1 becomes R2, R2 becomes R1. It becomes this, right? Look at this with that. They are just the same, right? What does it mean? It means the following. The spatial part is describing two electrons both are in 1s is symmetric with respect to interchanging the two electrons. Do you get this point? Okay. So this is symmetric, not quite what we want. The whole or total two electron wave function ground state helium must be antisymmetric. Should we worry? Well, not quite, because we still have a spin part to include into it. And once upon a time, maybe 2 weeks ago, we studied how to add two spin half angular momentum. Now, these are the two spins half of the two electrons. There is a spin singlet that is antisymmetric, the entangled up, down, minus, down, up. That is perfect. That is antisymmetric. Thereby, if we use this symmetric space part, multiply into the antisymmetric singlet, up, down, minus, down, up, the total wave function become the legal wave function, the proper one. And that's the only proper one that you can write down. Therefore, helium ground state is unique. Well, as we expect from many quantum mechanics problems, the ground state is unique. All right. So let's take a break now, and we will continue on with this point.